All right, we should get started. Somehow we've gotten to the last lecture. I don't know how that happened. Seems like it's never gonna get here, then all of a sudden it's here. Thank you for the toilet paper, whoever, I don't know whose this is. It's yours? I don't know. I'm not sure if there's some implication or something. I don't think I'll explore that any further. I don't know. You need toilet paper, there's some up here. We're going to move on today to problem solving, which is a somewhat neglected but interesting area in psychology. It's a little bit of a, kind of a poor cousin or something. Memory really dominates things. Perception should dominate things, but it's too hard. So a lot of people don't do perception, they do memory, because then I just have to give you lists of words or something. But problem solving could have been great and really interesting, but for whatever reason, it never really took hold. Now, I say this as somebody who did a whole bunch of problem solving / developmental research once upon a time, so maybe I'm just bitter. But problem solving is really pretty interesting, and it's one of those areas that we probably should have done more with in psychology. So let's think about problems. So problems are things that we sort of think about as the special case when you're stuck on something, right? Then you have a problem. But the problem-solving approach in psychology, in cognitive psychology, is much bigger than that. So a problem is going to be any time you are in one state, want to be in another state. It's just not clear exactly how to go from here to there, more or less. Okay, so it's very, very general. All right, so that's kind of the definition of a problem. You are in one state, you want to get another state, and the route isn't immediately obvious, clear, available, whatever. Somehow you've got to make some changes in order to make this happen. So super general situation in the biological sphere. Right, so how do you know when you have a problem? Well, it's a kind of a good question. What does it mean to know that you have a problem? You're often in a state. I mean, you're always in a state. But how do you know that there's a better state out there? It's a difficult question. It's not one we usually think about asking in psychology. Right? But you always think that there's a better state out there, right? You know that I'm in this state, and now there's a chance that I could go and do something more fun, more interesting, maybe more like get me some fuel, right? Immediately satisfy some needs. Somehow you're aware of that other state. But again, this impediment between you and this goal state is sort of this definitional core of problem solving. So an organism wants X, that is, wants to be in state X, but can't find X. That would be a problem. Sure what's happening there. All right. Oh, I know what I did. Can't, perhaps they know where X is, but they just can't get there, right? So that's a slightly different case. It's one thing not to know where something is. It's another not to be able to reach that location. You also might not know where X could be looked for. That is, you're trying to find something, but you don't even know where to begin the search. Another problem you can have is you don't know how to consume something, even though you have it in your possession. So you have a coconut, which is good news if you're on a desert island, but now you have to open it somehow. That's a very difficult problem without the right tools. Right, so problem solving is this very general idea. It covers everything from this classic from psychology being in a T maze. You know what a T maze is? The maze that's shaped like a T. So you start at the bottom of the T as the creature. Any capital T will do. And then in one of the ends of the T, of the cross piece here, there's a reward, and the other, there is no reward. You do that after a while, and the creature learns to go right or to go left, depending on where the reward was. So that's a T-maze, like the simplest maze. Foraging for food is another problem, really difficult problem. If you are living in the sort of natural world and you're let's say you're a squirrel and your job is to go and find food, right? As humans, we don't think about foraging as much of a problem because we go to the grocery store, right? So you go foraging to Price Chopper or something. Used to be harder here. There used to not be a Price Chopper. Foraging had to be done all the way in Tolland. But foraging for food for a creature living on the surface of the earth, it's tricky, right? Where do I look? You can have very human problems, right? Like sitting in a physics class and suddenly being asked to compute the torque of something. Oh, gee, what was the formula for torque again? How does that work? Navigating to Cleveland could be a problem, and so on and so forth. And there are so those of us who did problem solving, look at the ubiquity of this. This is fantastic. So problem solving is indeed ubiquitous, and it's done by all organisms. So all living things solve problems, we think. So from migration to hunting prey, avoiding predators, right? Those are all types of problems. So let me give you this example as kind of humans trying to show some problem solving abilities kind of from the human perspective, I think, which is something we'll talk about in a second.
At the Max Planck Institute for Anthropology in Leipzig, Germany, psychologist Joseph Kolb places a peanut inside a clear tube. How can the chimpanzee get the snack? She's never seen this puzzle before.
For 10 minutes, there's no solution inside. And all of a sudden, boom, they solve it. They have to understand that they can use the water as a tool. This is interesting because the water itself doesn't have any shade.
Using water as a tool seems like something we would do on a good day.
Yeah. So very clever. You get the idea. So why was that interesting to them? Well, because it's kind of like human problem solving. So humans have this idea that we are like the king of problem solving, and that problem solving in other creatures is, it ain't so great. So they are often looking at situations like this where the question isn't like, what would the creature do in its regular environment? It's, can they extend their abilities out into these very weird situations that they would very rarely encounter, right? So here, this particular, not sure what it was, chimpanzee maybe, figures out how to get the nut up out of the tube using water, and the scientist is very interested in that because, well, you think about it as a tool, right? Classified water now like it's a tool. Ooh, that's interesting. It doesn't have shape. Ooh, that's interesting. But the overall idea that somehow the problem solving gets assessed by them being like us in that, something we might do on a good day, as the commentator says, is a little bit of a anthropomorphic theme that scientists have tend to put on problem solving in the other species. Let me give you a bit of a counterexample, which isn't going to seem like a counterexample at first, from a very classic problem in problem solving, but also just in the real world in the domain of transportation networks. So transportation networks are indeed things like real everyday transportation networks. And there are transportation networks are all over the country. So from here, you can't really get anywhere without a car. But you kind of can, I guess, but it's really bad network, right? You got to ride a bus. But if you go to Hartford, you can pick up the train transportation network. That transportation network has been kind of worked out with the government's input, the company's input, who runs the trains, right? So it's a kind of a complex set of characters in there making decisions about where we're going to lay very expensive rail lines, how we're going to essentially take people's property away so we can lay those lines. Are very, very difficult to do and big investment. But the problem with transportation networks is a kind of a more fundamental problem. And it's about how one balances the cost of laying down those networks and the efficiency that you want out of the network. So it would be great from an efficiency standpoint if there was a rail line from here directly to New York City nonstop. That'd be awesome. Except it would, that would be totally baseless, right? Because there are so few of us here, and so few people from New York want to come here. It just wouldn't make any sense, right? So there's there's always this trade-off between, well, that would be great, super efficient for us, but the cost of actually doing it. So transportation networks, as a problem, is always trying to optimize those kind of two competing ideas. So this question comes up in things like, how should one optimally design railway systems, right? If you're into the mathematical end of this, you could ask, is there an actual optimal solution if we weight these two things, say, equally? Right? It turns out to be a very difficult problem. So here is a map of Shanghai and some surrounding cities, and the size of the dot corresponds to, at least when the map was taken, population. So the idea is, how do you connect those cities in a way that is maximally efficient and at the same time maximally cost effective? Right? You could connect everyone to everyone directly. That'd be one way to do it. Or you could do what is usually done and sort of decide that some are going to be like the hubs and some are not going to be the hubs. And so that's usually how it's done. And in fact, in that particular case, that is exactly how it was done. Some were chosen to be hubs and some not. Well, it turns out, now we get back to my anthropomorphize and explain, that if you give a cellular slime mold the same setup, okay, as the transportation network. Okay, let me explain what that means. By setup, I mean you say here. Let me go back one step. What the cellular slime mold does is it develops a network for consuming whatever is edible in like the immediate field. Okay, so maybe over a couple of maybe 6-8 inches. So you can manipulate what's there and how much of it there is. So it likes oats, it turns out. So you put some oats here, you put some oats here, right? And so what these very clever people did is they made the distribution of the oats exactly like the Shanghai region in terms of the population. See what I mean? And what they asked the slime mold to do is, what kind of network are you going to develop to consume these resources, to move them around? With me? So that makes sense? You see the analogy? So it's like oat transportation by the slime mold is like people transportation by the train network. Okay? Okay, so this is a single-celled creature, the slime mold. And of course, the transportation network is being designed by I don't know how many cells are involved. Many, many cells, many, many people, many, many decision makers, lots of engineers, smarts going into this, right? So it turns out that the slime mold develops the same transport network as more or less, as the governments and forces around the Shanghai region. Oh, I did. So forgive the beginning here, it's kind of weird. I'm not sure why it's being, there you go. So this has many more locations than that original map. But you can see how it's developing a transportation network. Consumption network, I guess, but it's the same principle. So it has a lovely balance of efficiency, robustness, just like we were. Okay, so why do I bring that up? Because it looks like other creatures, if you ask the question in the right way, do things that are super smart. Transportation networks is a really difficult problem, like a famously difficult problem. Other creatures can solve those problems if you kind of put it in the right terms for them. Okay. So this was a very clever experiment, right? To make it like match on to a transportation network that was famously good someplace, right? Show that it built a similar thing, right? Very, very clever. All right, so all that said, most problem solving work has been done. And so I'm going to tell you about some aspects for the remainder of the talk here. But keep in mind, at the back of your mind, that the humans aren't necessarily the only ones who can do sophisticated problem solving. So let me start with this example. It's a favorite example of people in the problem solving world. One of my favorite examples. And my favorite not just because I get to know the answer and you guys don't know the answer unless you look at it on the slide, and then you'll know the answer. But because it's such a beautiful illustration of one of these very mysterious things in problem solving. So let me start with this this grid. It's a 64 square grid. Okay, there's 64 squares there. It's 8 by 8. Okay. And the first question, just by way of illustration, to show you what we're doing, is can you cover the 64 square grid with 32 dominoes, where a domino can cover 2 of the squares at a time? Okay? Very straightforward. All right, so there are 32 dominoes. There are 64 squares. Can it be done? Yeah, simple, right? And immediately you're just like, well, of course it can be done. It's an even number going this way, right? So I can go 2 there, 2 there, 2 there, 2 there, right? No problem. Okay. Now just to make this a little more difficult, actually it's going to make it a lot more difficult, we're going to remove 2 squares from the grid. Okay. One on this end here, can't put anybody there, and one here. Okay, so if you're paying attention, we now have a 62 square grid. Can you cover that with 31 dominoes? Okay, and no, you can't go. The dominoes have to either go this way or that way. Okay, they can't. They're not going diagonal or anything like that. Have to cover completely, no overlapping. Okay. So now this very trivially simple problem, most people find becomes considerably more difficult. Even though you'd be hard pressed to say, like, why is this so hard now? Right, so does anybody think they have a good answer? Sorry, let me just. Right, so that, and then this, prove that it can be done or can't be done, is the kicker, right? It's one thing that, well, I think it can be, but it's another to be able to say why exactly it can or couldn't be. So this problem was famously given by Herb Simon, who's one of the Nobel Prize winner, founding father of cognitive psychology, to his partner in crime, Newell. And Newell, like, part mathematician, part computer scientist, super smart guy. He went bananas trying to figure out how to prove this. Notebook after notebook after notebook. Okay. Couldn't figure out how to prove it. Okay. So don't feel bad. It's very, very difficult if you don't feel like you can prove it. So let me now make a slight change, which is gonna maybe make it a little bit easier. So instead of the grid, we're gonna change this to be a checkerboard, an 8x8 checkerboard. Everything else is the same. And the question is still the same. Can you cover the remaining 62 squares, right? We're not doing the ones with red on them, with 31 dominoes, just like we did. Okay. And if you prove that it can't be done. So this version, it may not be doing it for you right now. This version tends to get much higher success rates. Anybody have it? If you just look ahead on the slides and then you look really smart. You don't have to. All right. Should I just tell you? So yeah. So this is very, it's still very hard. Don't get me wrong. So it shouldn't just like jump out at you. But it's now provable in a way that didn't seem available before. And that's what's so interesting about it. Okay, so let me show you the proof and then. Okay, so it goes like this. Here, it's gonna be like steps in a proof, like what do you call those? Statements or something in a proof, right? So the first statement is that each domino must cover one black and one white square, which has to be true. Right? So if we're going only horizontally or vertically, there's no way you can place dominoes, so that's not going to be the case. With me so far? Easy? But here's the thing. There are fewer white squares than black squares. We got rid of 2 white squares. Okay? So there's no way that you can cover the 62 squares with 31 dominoes because you're always gonna end up, you're gonna end up violating this must be true rule. See what I mean? Those two things are in conflict. So it can't be done. Right? But so why is it? So the mystery of it is how can just thinking about it differently, right? Because all we've done is think about it differently. We haven't really changed anything. Right? It's still the same problem structurally. It's just that we made alternating saturation in the squares, right? We didn't do anything like to the problem itself, but somehow changing how we're thinking about it allows us easily to solve it, right? And that's kind of the great allure of problem solving, is that you think it can't be solved, right? Or you think you're at a dead end, and yet you may suspect or even know that there's just something, if you just change how you're thinking about it, it'll be clear, right? It'll be solvable. And so that's why I like this problem so much, is because it continues to bother me that that's so easy to do, that this is so easy to do once you have that additional and not non-structural change to the problem. Let's put it that way. Okay. Solution makes sense? Yeah. Okay, this is called the mutilated checkerboard problem, which is a bad name for it because it gives away the solution. But anyway, it's called the mutilated checkerboard problem. So some people have tried to build like typologies or classification systems for problems. So this is going to be a little bit more mundane. So this fellow, James Greenough, proposes there are three major types of problems. One type he calls arrangement problems. These are problems where you have all the elements laid out in front of you. Okay? And your job is to order them or group them or rearrange them somehow so that they meet some criteria, right? So you've got a bunch of letters, for example, like an anagram, and your job is to rearrange them into a word. All right, so that's a classic kind of problem. All right, so that becomes school, for example. So arrangement problems are one of his examples. Another type of problem he calls an inducing structure problem. Here you're trying to find the structural relation that is sort of deeply embedded in the problem, or maybe just find the one that's intended by somebody. So analogies are like the classic iconic example of inducing structure problems. Right, so a storm is to rain as a virus is to illness or something, right? Oh, I have, right. As a virus is to snow, that's not ever going to be very good. As a virus is to illness, that's going to be the right answer. I've already given it away. But you could also use that a good distractor like hand washing, right? So the virus is related to hand washing. But it doesn't have that causal relation that you have at the top, right? Storm to rain. You usually think about that as a causal relation. So generally people would favor illness over hand washing. So this is often used on IQ kind of tests. So there are lots and lots of examples of this. I'll show you this very famous, but now kind of looks pretty old-timey kind of example. This is called a Raven's progressive matrices. And this is the kind of base algorithm up here, or base analogy, I should say. And now what you're supposed to do is choose one of these guys, one of these 8 to go in this spot. So there are relationships up here. All right. And now your job is to guess, well, not guess, figure out would be better. You could guess which of these guys goes here. Nasty, huh? Not so bad once you get a little practice with it. All right, anybody have an opinion? All right, so it's kind of interesting because you look at it for a while and you're like, oh, I see. There's certain things that are systematically changing across the rows, systematically changing across the columns. All right, and it's like you start to see, oh, you're playing with these features. It could be a lot of things, right? That's when you first look at it. It could be many, many things. Like, oh, wow, okay, because these are like that's a complex image. All right, so you have to start looking around to see like what the game is. All right, and so what the game is essentially saying, well, what are the dimensions in the analogy? Anybody have what they like? That guy? 5, right? Because every row has a square and we'll call that a diamond and a triangle. All right, so we know it's got to be a square, and then every row also has a bar. All right, all these bars are at the same orientation, so we need that bar, dark bar, I guess, at that orientation. I think that's right. Right, but they're hard. They're sort of hard because they're kind of so visually complicated. This is probably an easy one relative to some of them. They get really, really hard. All right, so another example of an inducing structure problem. The kind, again, you might encounter IQ test. The final type in Greenow's triad are called transformation problems. Transformation problems involve going from a particular initial state, right, that's given to you, to a particular goal state. So through some set of transformations that you may or may not know about in advance, right? So like what the right strategy is really kind of what they're after with transformation problems. Right? So oftentimes, other problems aren't going to specify the goal state directly. The Tower of Hanoi is a famous, you've probably seen these around, is a famous transformation problem where there are rules, but the goal state is actually very simple. You want to move these disks. These are disks on a peg just like this. Okay, but this one happens to have all the disks on it over here. Okay, so these disks all have to be put on this peg, but you can't ever have a larger disk on top of a smaller disk. Okay, and you can only make one move at a time. You can only go one step at a time. I think that's right. So it turns out that there's like a repeating pattern of steps that you can do that's optimal. Then there are lots of other things you can do that are suboptimal. That there are a whole broader set of things that just won't work. So there's like one line you can cleave to, then there's kind of a little bit of space around it. Yeah, you can screw it up, but that's not optimal. And then there's a bunch of other things that just won't ever get you there. The simplest thing to do is to distract the experimenter, okay, and then rotate them. Right, well then it would appear like you just solved the problem. Which is, you get the idea, right? So there, rules, goal, now you have to come up with the right set of transformations, which are like executing these moves. Okay, so as I said, here we have an optimal set of moves, right? And so in a way, what the researcher gets interested in is discovering this pathway through this possible set of moves. But lots of problems are like this, like math problems are generally like this. A whole set of math problems are more like our transformation problems. Right? Here's the initial set conditions. What I want to know is solve for x. Okay, but I'm not going to tell you how. But there are rules, and most at least higher level math, there isn't just one path. There are lots of different ones. The final problem type I want to tell you about are insight problems, which are maybe the most famous type. They're actually not part of Greenow's taxonomy of problem types. I don't know why he didn't include them, but he didn't. So insight problems are those kind of problems that you seem to be ruminating on for a while or working with for a while, and they suddenly are solved. Go from stuck to solution almost miraculous. And that has drawn obviously people's interest on it, right? So it's like, oh my gosh, suddenly I have it. And I don't know why. Many times you feel like you're making progress, right? But these aha moments are particularly nice. So as I said, not part of Greenow's taxonomy, right? So the solution comes suddenly, not incrementally. Sometimes this happens with the Tower of Hanoi, but generally speaking, the participant is aware of their progress or lack of progress towards the goal state. So it's not like you go, oh, I see. Sometimes they'll discover the strategy in a somewhat of an I see moment. So what people tend to say about these problems is usually the insight comes from relaxing some constraint that you think was in there that actually isn't in there. Right? You're assuming that this move can't be made, but oh, actually it can, or that route was closed, but actually it wasn't. Right? So they talk about that as relaxing an assumed constraint. The most famous, I think the most famous example of an insight problem, you probably already know the story, but I'm going to tell it to you anyway, is the story of the discovery of Archimedes' principle. So Archimedes was a very famous Greek physicist, working around 200 BC. And he was asked by King Hero II to determine if a crown King had obtained was actually gold, as opposed to like gold plated or some other metal that had been painted or something, right? So he wanted to know, is this actually a solid gold crown? Without like harming it. Right, so this is not the actual crown, but it is a crown, just sort of by way of visual aid, right? So the density of gold was known at the time. All right, so that's the beginning of what might help, right? So if I know the density of gold, I could figure out some things. But I need both mass and volume to compute the density. Okay, so the mass was no problem, and I know what density I'm shooting for, but the volume, what's the volume of that damn thing? Well, if it had been a square, we would have been in business, because computing the volume of a square, I knew how to do that, or a circle, or other things, right? But this object, right, it's not computable. And so that was a problem, and the king wants the answer. So Archimedes has this insight moment, which is the point of the story. So he's lowering himself into the bath, and he notices that the water is being displaced by him. Right? Water is not compressible. It doesn't get crushed. It doesn't compress. It just gets displaced. So if I want to know the volume of something, Archimedes' volume, I could just see, well, how much water did Archimedes displace? If I want, and this is of course the insight, if I want to know what the volume of the crown was, all I had to do was see how much what the volume of the water displaced was. So the volume of displaced water equals the volume of the crown. And that was a way to measure it. So that is a perfect example of an insight problem, which allowed him to complete his task. Okay. So that sort of thing is something that happens once in a while. It doesn't happen all that often that you discover something. But when it happens, it's a bit of a mystery how one comes to a totally new understanding of something. That volume can be determined this way, for example. Questions on any of that? Probably the last thing I am going to tell you about, maybe there'll be one more, but maybe that'll be the last thing, is a phenomenon called functional fixedness, which is very famous. And very frustrating when it happens to you. It is the opposite of insight. It is being subject to an assumed constraint that then prevents you from solving the problem. You think that certain things have to go in certain kind of categorical slots. And by doing so, you limit what those things can be used for. It's called functional fixedness. So once you categorize a particular item in your problem-solving array, or whatever it might be, categorized into its role, it's hard to figure out what else you might use it for. Hard to sort of open it back up. So the most famous and the original example of this is something called Dunker's candle problem. And it is a kind of problem is it? It's a transformation problem, I guess. Yes, it is. Right? Because you have a goal state, which is to mount a candle on the door at eye height. Right? I suspect that no one in the participant pool was actually asked to mount a candle anywhere. Not the sort of thing we usually ask people to do anymore. But back in the day, this was the sort of thing you could do. And there were matches involved as well. Would not get through the IRB anymore. So they're given a set of materials. And these are the materials. You have a candle. You need that. You're going to mount it. You have a box of tacks. And you have a set of matches. Okay. Don't give participants matches too often anymore. But there are two conditions under which these materials are presented to you. One is like this. Right? The tacks are in the box. And in the other, the tacks are not in the box. Okay. With me so far? So in this case, the box is a container for the tacks. In this case, the box is more likely, at least, to be categorized as some part of the problem-solving procedure. Okay, so what happens is that when the tacks are in the box doesn't get used in solving the problem. Right? And so it's very hard to make the candle stick to the door with just a bunch of tacks. Right? You can imagine what people kind of trying to build a shelf out of the tacks, or trying to push the tacks into the thing and then push the tacks into the door. It's just not going to work very well. But if you use the box, right, then you can use the box as a shelf. Okay, so what's the functional fixedness? Well, the functional fixedness is that the original categorization of the box fixes it as a container for the tacks, not one of the things available to me in this problem, right? So that categorization is functional fixedness, or at least causes functional fixedness. When the tacks aren't in the box, well, now I can use it, and the problem is easily solved. All right, so that's one example, the earliest example, but people do this all the time. Right? You'll get into a situation and you'll have something there present capable of solving the problem, and you won't use it because you're just not thinking of it as part of as one of the potential solutions or contributing to the solution. What do I got? Oh, I got a couple. All right, so let's talk about just some theoretical issues here. So generally, problem solutions end up being constrained by the nature of the problem itself. That is, only some things can be done, other things can't. I'm encountering this in a particular setup with these moves available. And then there's also the nature of the problem solver themselves. So there are limitations on human cognition, for example. So you can only do so much computation so quickly. You can only remember so many things at once. People in problem solving like to think about the problem solutions as kind of moves in a space. So a favorite way to think about problem solving is that you are starting off in a space and moving through the space, but kind of like this point of view camera here, you're not able to see the entire layout. Right? All you're seeing is what's immediate, what the immediate choices are in front of you. Right? You can't get the overview of the space. Right? So if you're in a maze, well, that's true. You're literally moving through a space, right? So that's kind of one way to consider this metaphor, right? But now it's almost not a metaphor. But lots of problems can be considered this way, that there are moves through some problem space. It may not be just a 2D space. It may be a many D space. Right, so we think about that usually as some version of a state space. So the state space is constructed all the possible states that the problem can take. And you end up moving through that space somehow as you're doing your thing, right? And so that's a very powerful and general way to think about problems. So one of the things in the space that would be kind of highlighted, I suppose, are these things called subgoals. So let me give you an example of subgoals with a simple transformation problem. Right? So the nastiness of the 2-digit multiplication. No one likes 2-digit multiplication, but we all have to do it once in a while. So the nicest way to solve problems like this are just to recall the answers from memory. Okay, so that's one way you could do this. And if you know, if you have memorized your 16 timetables, which you probably haven't, you know this right from memory, like, oh, that's no problem. And then you're done, right? So that's problem solvers always end done. So recall from memory, done. You could also do a different strategy. This strategy has some sub-goals. First, you break the problem into 2 problems, 10 times 18 and 6 times 18, right? That seems acceptable. Hopefully that seems like a reasonable way to go. All right, solve each one, add the products, and then you're done. But you can see all the sub-goaling in there, right? So sub-goal 1, sub-goal 2, I guess really the solving of them will sort of fold back in there. But then you have another sub-goal, which is add the products. Oh my goodness, right? That's a lot to remember. That's a lot to hold on to all in one shot. You could also compute 16 times 20, right? And then subtract 2 times 16 from that product, and then you'd be done. I'm not saying it's any better, it's just another way to go. Also with sub-goals. So one of the weirdo mysteries in problem solving is, how do you know what your best choice is there? How do you know how to traverse this particular set of moves through the problem space? How do you choose? Like, how do you go, like, well, maybe I'll try this. Oh, turns out I don't know. That was bad. Okay, so maybe I'll try something else. Right? But maybe this one would have been better, right? So how do you make your decisions amongst those is a major issue in problem solving. So somehow you need to know, like, the likelihood of success of each strategy, right? And then the speed of execution of each one. So people have spent a lot of time trying to figure out how humans are able to do these things, especially when faced seemingly with all these choices every time they do them. Okay, so this all works for things like where the paths are kind of well worn. This kind of reasoning works because you can imagine that, well, I've been down this road before with the 16 times 18, and I don't remember any of those things, so I better choose one of the other paths, right? But what about when you're faced with obvious choices about what you can do, but you haven't ever really dealt with problems of this type before? People still make choices, and they tend to make pretty good ones. So this is one of the areas of problem solving that people are still working. All right, I am going to close up there. Thank you very much for your attention, and we'll see you on Wednesday.